Howdy, let's go ahead and move into section 2 of chapter 9. We're still talking about testing claims, and now we'll do some specific examples with population proportions. So in this section, we'll talk about stating and checking the conditions for random selection, the 10% rule, and the large counts conditions, all related to performing significance tests about population proportions. We'll perform a significance test about a population proportion. We'll interpret the power of a test and describe what factors affect the power of a test. And we'll describe the relationship among the probability of a type 1 error, the significance level, the type 2 error's probability, and the power of a test. Recall in the last section our basketball player who claimed to be an 80% free throw shooter. In an SRS of 50 free throws, he made 32. His sample proportion of made shots was 32 out of 50, or 0.64. That's much lower than he claimed. But does it provide convincing evidence against his claim? We discussed in the last section that it probably did, but now let's put a little more definitive mathematics behind it. So to find out, we're going to perform a test of significance, testing HO, the null hypothesis, that P equals 80. With HA, P is less than 80, where P is the actual proportion of free throws the shooter makes in the long run. Recall, we've got HO and HA. This is always in terms of a parameter, so P. The null hypothesis is always equal to, and the alternative hypothesis is either less than or greater than or not equal to. And then we need to define what P is. In this case, the actual proportion of free throws he makes. In the beginning of chapter 8, we introduced 3 conditions that we need to meet before we construct confidence intervals for proportions. The random rule, the 10% rule, we sample without replacement, and large counts. We have to do the same things when we're going to carry out tests of significance. First of all, we always want the data to be random. We want the data to come from a well-designed random sample or a randomized experiment. This helps us avoid bias. When we sample without replacement, we want to make sure that we sample less than 10% of the population. And finally, we need the large counts rule so that we can make the sampling distribution approximately normal. And large counts applies to proportion problems by having at least 10 successes and failures. N P naught and N times 1 minus P naught greater than 10. So what does that mean? Well, if the null hypothesis 0.8 is true, then the player's sample proportion of made free throws would vary according to a normal distribution with a mean of 0.8 and a standard deviation of the square root of P times 1 minus P over N. So 0.8, 0.2, and 0.5. Note that this is a P, so it's this 0.8. It's not the P hat that we got from his trial, this 0.64. It's actually P. So there's my standard deviation. The significance test will use sample data to measure the strength of the evidence against HO. So here's some principles that apply most of the time. The test compares the statistic calculated from the sample data with the value of the parameter stated in the null hypothesis. The values of the statistic that are far from the null hypothesis in the direction specified by the alternative hypothesis give evidence against HO. The test statistic measures how far a sample statistic diverges from what we would expect if the null hypothesis were true in terms of standardized units. So this is the same concept that we used with standardizing before. It's the statistic minus the parameter divided by the standard deviation of the statistic. The test statistic says how far the sample result is from the null parameter value and in what direction on a standardized scale. In what direction means if it's going to be positive or negative. We can then use that test statistic to find the p-value of the test. Let me show you what I'm talking about. In our free throw shooter example, the sample proportion, 0.64, is pretty far below the hypothesized value of 0.8. So when we standardize, it's the statistic minus the parameter divided by the standard deviation. Now that 0.0566, that's this number right here. So this tells me 0.64 is almost 3 standard deviations below, because it's negative, the expected value of 0.8. The shaded area under this curve shows the p-value. And it shows here the corresponding part on the standardized normal curve. So you see that it's just basically exchanged this scale right here to standardized units. If I use my table of standard normal distributions, I can find that that area is 0.0023. The area to the left of 0.64 is 0.0023. That's called the p-value. So if HO is true, if he really is an 80% free throw shooter, there's only about a 2 in 1,000 chance that he would be so unlucky to make only 64% or less. To perform a significance test, we state the hypotheses, we check the conditions, we calculate a test statistic, we find a p-value, and we'll draw conclusions in the context of the problem. Sometimes we'll use a 4-step process. Here's what the book uses as a 4-step process. First, what hypotheses do you want to test and at what significance level? Define any parameters you want to use. Plan. Choose the appropriate inference method and check the conditions. Do. If the conditions are met, perform the calculations, including the test statistic and the p-value. And then finally, conclude. Make a decision about the hypotheses in context of the problem. State, plan, do, and conclude. When the conditions are met, the random, the 10%, the large counts, then the sampling distribution of p hat is approximately normal with mean. The mu of p hat is p, and the standard deviation of p hat is the square root of p times 1 minus p over n. The z statistic is approximately the standard normal distribution when HO is true, and p-values therefore come from that table of standard normal distributions. Choose an SRS. This is a one-sample z-test for proportions. So choose an SRS of size n from a large population that contains an unknown proportion p of successes. To test the hypothesis p equals p naught, compute the test statistic. Then find the p-value by calculating the probability of getting a z statistic this large or larger in the direction specified by the alternative hypothesis. In other words, this middle one right here is what I was using for my example because we hypothesized that p was less than 0.8, this down here. Now, if the guy had done really well and made, say, 95%, he might want to claim that he's better than the 80% standard his coach said, and he would test it this way. Or maybe it's a two-sided alternative. The alternative is that it's not equal, and we end up with a symmetric graph on both sides here. The p-value in a one-sided test is the area in one tail of the standard normal distribution, the tail specified by HA. In a two-sided test, where we've got the not equal to, the p-value in such a test is the probability of getting a sample proportion as far as or farther from p naught in the direction of the observed value of p hat. As a result, you have to find the area in both tails of a standard normal distribution to get the p-value when it's a two-sided test. So why do confidence intervals give us more information? Well, the result of a significance test is basically a decision to reject HO or fail to reject HO. When we reject HO, we're left wondering what the true proportion might actually be. And a confidence interval can help shed some light on this issue. Here's another example. Taeyeon found that 90 out of a simple random sample of 150 students said they had never smoked a cigarette. The number of successes and the number of failures in this case is 90 and 60, both of them more than 10, so we can proceed with the calculations. As we learned before, our 95% confidence interval would be p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. Since 90 out of 150 is 60%, this is 60 plus or minus 1.96. That corresponds with a 95% confidence interval. 0.6, 1 minus 0.6 over n, that's 150, square root it, and then I get this interval. So I'm 95% confident that this interval, the interval from 0.522 to 0.678, captures the true proportion of students at Taeyeon's high school who would say they've never smoked a cigarette. There's a link between a confidence interval and a two-sided test. The 95% confidence interval gives an approximate range of p's, of proportions, that would not be rejected by a two-sided test at the 5% significance level. 5% significance because it matches with 95% confidence. Those add up to 100%. In other words, a two-sided test at a significance level alpha and the corresponding confidence interval gives similar information about a population parameter. Now, let me show you what I mean here. If this was my interval, any value in here would be believable to you. So if I made the claim that 55% of the students would say they've never smoked, and you found this interval, you would say, oh, yeah, 55, that's believable. If I said 65, you would look at this interval and say, yeah, that's believable. On the other hand, if I said 70, you would say, no, I don't really think it's that high. Or if I said 50%, you would say, no, I don't really think it's that low because I'm pretty confident it's in here. So sometimes we use confidence intervals to answer the questions that a significance test would tell me. A significance test makes a type 2 error when it fails to reject a null hypothesis that is really false. If the null hypothesis is false, we ought to reject it. But sometimes we fail to reject it, and that's a type 2 error. There are many values of the parameter that make the alternative hypothesis true. So let's just concentrate on one of those for right now. The probability of making a type 2 error depends on several factors, including the actual value of the parameter. A high probability of type 2 error for a specific alternative parameter value means the test is not sensitive enough to detect that alternative. A high probability, let me say it again, a high probability of a type 2 error. Type 2 errors are bad. That's why they're called errors. So a high probability of that for a specific alternative parameter value means the test is not sensitive enough to usually detect that alternative. The power of a test against a specific alternative is the probability the test will reject HO at a chosen significance level, alpha, when the alternative value of the parameter is true. Now, this concept of power and type 2 errors combined with alphas and particular alternative values can be a little bit challenging to understand. I encourage you to watch perhaps one of my other videos where I work through concrete examples of power and show you how all of these things interrelate. So let's talk about a potato chip producer who wonders whether a significance test at P is 0.08 versus P is greater than 0.8 based on a sample of 500 potatoes has enough power to detect a shipment with, say, 11% blemished potatoes. So here's what this means. He's gonna buy these potatoes unless there's more than 8% bad ones. Now it turns out, unknown to him, but this new truckload has 11% blemished. Will taking 500 potatoes be enough to help him realize that it's not 8, and in fact it's something bigger than that? So in this particular case, we've got this graph. Notice it's centered around 0.08. The alpha level at 5% sets this bar right here. In this case, a particular type 2 error is to fail to reject 0.08 when 11 is the truth. When this curve is the truth, if I'm outside this fence, I reject HO. That's actually a type 1 error. That's that based on that 5%, this level of significance. But if the truth is 0.11, I actually get another curve over here. Notice how this is just superimposed. That line stayed the same. But here's the truth. Now, if HO is false, a decision to fail to reject is a type 2 error. If I keep believing this, because remember, if it's 0.11, this is false. So continuing to believe this is a type 2 error. Over here on the other side of that fence is the power of a test. This area in here is the power, which is 0.75. This is about 25% for this problem. This is about 75%. So what this means is, if I use a 5% significance level, and I sample 500 potatoes off of a truck that has 11% bad ones, there's a 75% chance that my sample of 500 potatoes will be bad enough that it will tell me to reject the idea that 8% of them are bad and think that it's more than that, thereby not purchasing the truckload and making a correct decision. Conversely, there's a 25% chance that I'll keep believing 8% and end up buying the truckload with too many bad potatoes. The significance level of a test is the probability of reaching the wrong conclusion when the null hypothesis is true. The power of a test to detect a specific alternative is the probability of reaching the right conclusion when the alternative is true. We can just as easily describe the test by giving the probability of a type 2 error, sometimes called beta. So beta and power add up to 1. The power of a test against any alternative is 1 minus the probability of a type 2 error for that alternative. That is, power is 1 minus beta. Beta is the probability of a type 2 error. Alpha is the probability of a type 1 error. So in this section, we learned how to state and check the random 10% and large counts conditions for performing significance test about a population proportion. We talked about performing a significance test about a population proportion. We discussed interpreting the power of a test and describing what factors affect the power of a test. And we described the relationship between the probability of a type 1 error, the significance level, the probability of a type 2 error, and the power of a test.